So we are doing singularity discontinuity functions. I'm going to split everything straightforward and fast. Okay. So then singularity, what we've been doing so far is that most of the times you see a beam, and then the loads on it is actually throughout the entire beam. So you see this particular one here, the load, which is a uniform distributed load, is acting on the entire beam, right? So for cases like this, you don't need this discontinuity functions or the singularity, Macaulay, whatever, right? But there are some times where you have certain loads at particular points. What the discontinuity is saying is that let me what the discontinuity is saying is that you are not having the same forces throughout the entire beam. So like when you look at this particular one, I'm having the same force on it. So we are basically saying there's a continuous beam, something like that, right? But if you come to this particular example, what is happening is that if I look along the beam, there's the only side where the force, not necessarily like it should be one, it could be more than one, it could be multiple things, right? Along all this side, they are the same thing. There's no force acting on it. Let's say even if I introduce, let's say uniform distributed load here, right? It will still be a discontinuous beam, right? And then one way to solve is using the discontinuity function, because I'm having, what's the name? Aside the fact that I'm having the uniform distributed load acting on the entire beam, right? This acting on the entire beam, right? I have a force that is not acting on the entire beam, but acting only at this side, right? So that's why we are saying this particular one is discontinuous, right? And this right here is continuous, right? Yeah, so that's the difference. And then one way of solving the discontinuous beams is by using the singularity functions, right? Sorry, the discontinuity function, that's how they are called, right? Discontinuity functions. And then one thing about them is that we usually combine two functions to describe the whole thing, right? But then the basic thing, mostly the load that we have on the, for this particular example, the load that we have, the load that is that we'll have in a beam, or the possible load that we have in a beam, are these, right? Where we have moment, right? Where we have moment, a minute. Where we have moment, right? A point load, and we have a uniform distributed load, right? And a linear distributed load. These are the possible loads that we could have, right? And then each and every one of them has a way of representing it. And then so we look at that. So what we have right here is the basic unit of whatever we call the discontinuity function. Before we come to that, let's talk about the singularity and then the Macaulay, right? The Macaulay is basically representing moment, what do you call it? Concentrated moment, and then the concentrated loads, right? And then the Macaulay, this was singularity, concentrated moment, concentrated loads, right? And then the Macaulay, concentrated moment, concentrated load, that's for singularity. And then the Macaulay talks about distributed load, which could either be uniform distributed or linear distributed. Combining these two is what actually gives us the discontinuity function, right? So the discontinuity function is basically bringing these two together. Are you okay? So it's just a build up on the two, right? So MP moment load, concentrated moment point load, uniform distributed load, linear distributed load, and these are what we have here, right? So these four from the singularity, and then the from the singularity and the Macaulay functions are what come together when you write the function together, and we end up getting the discontinuity function. Are you okay? And then the basic unit of the discontinuity function is what we have in here, right? This whole thing here, and then we'll explain every term to see what's actually happening, right? So then we have when we look at it, we basically have plus or minus here. This plus or minus is basically the direction. Depending on the convention I use, if you are solving a particular problem, when you choose one convention, you stick to it, right? So let's say if I have let's say all these ones are pointing down, right? These ones are pointing down. So if I decide to use a moment, let's just put a coordinate system about here. Let's see. Say a coordinate system is here, right? Let's see here. This is just an example, right? Okay, so if I'm using this, and then I choose the convention that my down force is plus. If my down force is plus, if my down force is plus, wait, let's go by the common one. I'm just trying to. If my up force is plus, right? meaning that our force is plus, and I'm using this particular one, meaning that this way, this moment here, there's a force, there's a moment, meaning this moment here will be a plus, right? If you go by this way, because if I have a distance like this, and then this force is up, and then let's say from this distance here to about here, the moment, and then let's say there's a moment about here, or let's say even a force about here, it will end up 10 this way, right? So that will be in the same direction as this, which is a plus, right? So you choose a conversion and then you stick to it, right? Choose a conversion and you stick to it. So then if you choose this one, meaning that your down will be negative for force, and then your this way will be negative for your moment. Are you okay? So now we've established this as well. So now that we have this, we know the plus minus that's in front of it. The next one is actually the magnitude, which is what we've written here. Where we have this, and then we have the load inside, right? This is basically the magnitude of whatever it is that we are talking about. It could be any load, any of these four. It could be moment, consider moment, point load, uniform distributed or linear distributed. Any of these four is what we put here, right? And then let's see. The next thing to talk about in this particular equation, which is the basic, this one here. A minute. Then again, I'm going over this. This is the basic unit of the what do you call it? The discontinuity function, right? Okay. And then we spoke about the plus or minus. We spoke about what we have here, right? With the load, could be any load, right? So the next thing, we know x is just there, it doesn't change, but a here is the next thing, right? So that's what we do. What a talks about is actually the starting point of the load, right? So let's see, this is the coordinate system for this particular one. Let's see this particular example here. This is the code. Oh, this particular one here, this is the coordinate system, this is the origin, right? So what it's saying is that if I'm trying to transform, if I want to find the equivalent of this, let's say uniform distributed load here, this blue one, right? I'm trying to transform it. Where does it start? It actually starts at the origin, right? So if I'm representing it, I'll just say x minus 0, because that's where it starts, right? But then we are not done, we're left with the last term, which is the n here, right? This n. This n is the last term. And this n is constant, right? And it depends on the load, right? It's load dependent. Depends on the load. Okay. So we'll go through that in a minute. And then there's something that are fixed, because they are functions, they've been predetermined in a way to make the work easier, right? So this n here is what we are having here, right here, right? So we are saying that if it appears to be have a moment, the n is minus 2. If it's point load, minus 1. If it's a uniform distributed load, 0. And if it's a linear distributed load, s 1. Are we okay? Yes. So that's it. So basically we've defined everything in the basic unit of the discontinuity function. Are we okay? Yeah. And for each and every one of them, there's a way of representing each. So we'll take an example and then see how we go about it. So let's see. Take an example. Let's see. Take an example. Okay. Okay. Oh, let's before I finish. One thing about the the discontinuity function is that you see we said that this a here, this a right here is basically the starting point of the load, right? Another thing is that whenever you start it, it assumes, because that's what the function does. The function assumes that wherever I start, it takes it to the very end. Are you okay? We'll talk about the other one later where it doesn't go through the entire beam, it doesn't end at the entire beam, but you find a way to adjust it to make sure it makes sense within the function or the equation, right? But I see is whenever especially for the uniform distributed, uniform distributed for this w, sorry, the distributed loads, yeah, especially for the Macaulay, for the w and then keys, right? Whenever you start it, it assumes that from the start it goes to the end. So even if you put a 0 here, or whatever the position it is, it just sends it to the very end. There's a way to do that to adjust it. Are you okay? So now we have talked about that. Let's look at how to write the discontinuity function for this particular example. What happens is that for discontinuity, we are basically expressing everything as what? Loads. That's why we wrote load here, npwk, right? Set the meaning for each. So this is what happens. We are saying the load is a function of what? Of x, right? So when we're writing it, we go this way, w and then x, right? And then this is the basic form. We'll bring it here so we know we're actually flowing it. Okay, a minute. Clean this up. Then again, the n constant, the n's are constant, right? This particular n here is constant for, and we have a value for it for each and every load that is actually used, right? That actually can appear, right? So we're going to use this example, looking at what's right here to see if we are on the right path, right? Check up what we are doing. Okay, so this is what we are doing. We have a w, this is the load function, right? This is continuity load function, and then we have a plus or minus here, right? So basically you can start from anywhere, but let's start from the origin, and then we're going to start from the origin here and move this way, right, and clear everything up to see if we actually get the right function, right? So this is what happens when you start from this point. What are the forces there? The load, to be particular. So let's see, we can start with this. Let's use this here. Okay, so when you are at this very point, we have two things. First of all, we have this 75, right, which is a what? Looking at, it's actually pointing just one, so it's a point load, right? So what did we say about point load? Plus or minus. What was the convention? We are choosing this, the up is positive. So if up is positive, meaning that we are saying this way is positive, right? Let's see if that's what we did. Yeah, if this is positive for force, then this moment here too is positive as well, right? That's the convention we are using. Plus the convention we are using. This is a plus. Okay. Yeah, so we move on. So when we start at this very point, right, this is what we are saying. We have two things there. We have this force, it goes down here, it's already there. We have this force and we have this uniform distributed in yellow, right? So if we represented a force, is it plus or minus? It goes down, so negative, right? And then what again? We go to the load. The magnitude of it is what? 75, right? And we have the bracket here. This is it. We are going by this, right? Because we've established that already. And then we have x, it doesn't change, right? And then what do we have? Let's minimize this so everything will fit. Okay, x, right? What's the next thing we have? A minus, it doesn't change. We are saying a is where it starts. What does this 75? What does it start? Start at, and this is the origin, right? This is the coordinate system. This is the origin. So we are saying it starts at 0. And we have, what's the power? The exponent. The next thing is the n. For p, what did we see? We said p is minus 1, which is right here. So we put it there. Minus 1, right? What's the next thing? There's something else that starts at this position, which is what? A uniformly distributed load, right? Is it up or down? We said this up. If it's up, is positive, right? So this positive, which is showing here. So you have a plus. You go to the load of it. Was it 35, right? This side we are looking at this portion of it. We are seeing this one, this point up, which is this value right here. So it's all 35. Now the bracket, we have an x, and what was the e for it? Where does it start? Starts at 0, right? So minus 0, and then what's the n? It's a uniform distributed load, which means w, right? And w is 0, right? Uniform distributed, w is 0. What do we have next? When you move along this, we are trying to move along this side. You move, and you get to meet who? This particular 60 here. Is it pointing up or down? It's down, so negative, right? Sorry. down is negative. Down is negative. Let me write this out well. Down is negative, right? Yeah, now you're looking at the 60, right? You're looking at this right here. You're looking at the 60. For the values of the n, is important that you have them here, but it's a conversion. It's something that is used when you're using the discontinuity function, right? So now we're on the 60, right? 60 is pointing where? Down, so negative, right? Now we are looking at the, let me minimize this. Okay. 60 is down, right? Which is right here. And then what again? We are looking at the load. The load is 60, right? We have this, we have x, it doesn't change. We have an 8. Where is it starting? It's starting at what? 2.5. So that's about it, 2.5. And now we need the n. Right, this 60 here is a point load. P is what? Minus 1 here. Right here, that's what we see, minus 1. So you put a minus 1 here, right? Minus 1. Minus 1, right? What's the next thing? Then again, at this particular position, there are two things. This moment here, there's a moment, another moment here with action on it, right? And what's the direction? Can we tell that? We choose the convention that this particular direction is positive, right? So if this particular direction is positive, this one is in the opposite direction, so it means it's what? Negative. So if you're actually trying to turn, this one goes this way. Wait, are you sure it's negative? So let's see, this goes this way. The particular one goes this way. Looking at it, it's the same direction as this, so it's what? Positive for that particular moment, right? So a plus. And now we are looking for the load of it. We are saying the load is 120, right? So we have 120. You have the bracket. You have x, right? And then minus. What's the a? Where does it start? It starts, or where is it situated? It's actually a concentrated at the point. We are saying that's from this origin here. It's actually 2.5. So 2.5, right? 2.5, and it's a moment, right? A moment, what's the end value of it? It's 1 minus 2. That's what we have here. Let's see this. Minus 2, this right here. So now we put that there, and then you have a minus 2. Is there anything else to represent? Now we go here, right? And if you move along this side, you get to see that there's nothing else that we get to represent, right? Is there anything else? Yeah, there is. One thing is that because we have what's the name? A support here, which is a fixed wall. What happens is that you can turn that to a reactional load, a reaction, which will be something of this sort, right? So we have this was C, right? So we have dy, right? Yeah. One thing is that because we are just using that as an example to write the entire discontinuity equation for this BIM, we're not actually trying to solve it, so we're not able to even get the reaction force, which is a dy, right? But we are just writing this to see how it's written, how the whole function is written. So looking at this point up, so we have a plus. If we're to know the value of dy, we put it there, right? So we have the load. Now we have into bracket, and you have minus, right? What's the a? Where does it start? It starts here, but the coordinate system starts here. The coordinate system x start and goes up to this side, right? So is this 2.5, right? Plus this 3.5, that gives us what? 6, isn't it? Yeah, 6. So we end up getting 6 there. And as well, it's a point load. Are you okay? It's a point load, meaning that if it's p, then the exponent or the n, right? This n right here, this n in the original equation that we had, the basic unit for the discontinuity function will end up being what? Since it is since it's a p, to end up being what? Minus 1, right? So we have minus 1, right? Then again, you remember that this side here was actually what was the name? What do you call it? It's actually a cantilever. It is a fixed end, right? So if it's a fixed end, if you're able to, you can go back and check. There's there's a particular discussion on the endpoint. We got to know that particular endpoint when we have a fixed end like that. Let's see, we have a fixed end at this like that. At that particular point, we know that what do you call it? Slope is 0. I'm just using this as a way to revise. You know, slope is 0, and then what again? Oh, deflection is 0 and then slope is 0. And then if these two are 0, what is actually preventing the beam at that point from being deflected is actually this v. So there's a v there, which we have it to be at dy at this force at this point, right? And then if the slope there is 0, there's something preventing the beam at that side from bending, right? So at that point you have an m which is not 0, and then so meaning that the v2 is not 0, right? So at that point represent there with another moment. So just at this point, which is the end of the beam, you have another moment here, right? Moment, right? So let's see how many we are done with the dy. The last thing we have is the m, right? M. Okay, so let's see. So when we look at this m very well, right? If it were to be a bend, the beam will actually at that end there, at that very end like this. If this is the original position, the beam were to bend at that particular point, it bends this way, but at that point it doesn't bend, right? So there's something preventing it from bending. It's a moment of this way, right? Prevented from bending at that point. So we get to see, say the moment there, there's a moment there, right? So there's no bend there, but there's a moment there. So this I represent it. What's the direction? We choose this one to be a positive, so that way is one negative, right? So we have a negative. We are still going by this right here, right? So the direction is negative. What do we have next? We have the magnitude, right? We don't know it. If we have done the forces and everything, we have found it. But this is an example to just see how we write the discontinuity function for a beam, right? And we have x bracket x, and where does it start? Actually start here. So the starting is from the origin to here is our 2.5 plus 3.5, which is 6, right? That's 6. And then what's the end of it? Now we are left with the end. What's the end? For the loads, each of them has their own end, right? For m is 1 minus 2, right? So here becomes minus 2. Yeah. So there's a way of writing the discontinuity function. So this right here, whatever it is that we've done here, this is the load equation for this discontinuous beam. This is the load equation. So this is what the discontinuity function does, combining the singularity and the Macaulay functions. Yeah, so there's it. All right.